Hi, I'm Luis and I'll be talking about our new paper, Deep Compression for Dense Point Cloud Maps. Perceiving and mapping the environment are one of the key tasks in autonomous driving. Therefore, LiDAR sensors are widely used, which are able to generate 3D point clouds of the vehicle surrounding. Modern scanners typically record around 100,000 points per sweep at a frame rate at 10 Hz. On the one hand, this enables us to perceive and map the environment with a very high spatial and temporal resolution. But on the other hand, this requires special techniques to handle this huge amount of data. Online transmission or simply storing the point clouds on the vehicle is not feasible without further processing. If we want to utilize the 3D point clouds also later, for example, to generate a global 3D model or sharing, we need efficient compression techniques. Beyond single-scan compression, I can see two major possibilities to further compress the data. The first one is to exploit the temporal correlation in the measurement process. Let's look here at a series of scans. We can clearly see that subsequent scans look pretty similar. We can now use, for example, modern video compression techniques on the range image representation to explore those similarities. A drawback to this method is that it is very hard to compress data from multiple sources, like multiple sensors or even from different vehicles. A more general approach is to exploit the geometrical relations. Real-world and especially man-made environments have a lot of structure. If we look here, for example, on the right image, we see that most points lie either on planar surfaces, like streets or walls, or form recurring objects like cars, poles or trees. The most intuitive way for me would be to use this prior knowledge, create a shape database with some geometric primitives like planes and common objects like cars, trees, humans and so on. So that instead of saving all points from a certain car, we can simply store the ID of the corresponding car template in addition to its pose. The problem here would be to create a complete database which covers most of the cases. Even objects of the same class can differ a lot. Trees or cars, for example, come in a wide variety of shapes. But maybe we can find an automatic data-driven way to search for common geometric patterns. And for this, we propose a deep neural network in the form of an autoencoder. Our encoder computes a compact feature representation of the point cloud, which can then be stored or transmitted or later be used by the decoder for reconstruction. So the objective we want to achieve is that we want to extract a lightweight feature representation from which we can reconstruct the point cloud as accurate as possible. Let's look at our proposed architecture. Our encoder subsequently reduces the number of points and computes for each point a feature based on its local neighborhood. The last layer of the encoder projects the features in a lower dimensional space to reduce the memory footprint. The decoder consists of 4 deconvolution layers, which subsequently upsamples the point cloud based on its features. For computing the features, in the encoder we use kpconv, which is a continuous convolution for point clouds. It does not require any discretization like voxel grids or octrees and works on the points itself. It defines the convolutional weights on some specific kernel points from which the continuous weight space can be interpolated. For the decoder, we propose a 3D continuous deconvolution operator. We need to restore the point coordinates based on our feature descriptors instead of taking the points from the source point cloud as usually done in segmentation. Our deconvolution blocks consist of 2 small MLP networks that operate on each point individually in the form of 1 deconvolutions over the feature space. The first network on the top is a feature propagation network, while the second network predicts a translation vector for the new point coordinates. So, for each point, we create a new point and new feature based on its old feature. Having multiples of those blocks, in this case 3, upsampled the point cloud by this factor. Now, let's see which potential our network has to compress the point cloud data. For saving the raw point cloud, we need to store n times the x, y, z coordinates, where n is the number of points. Our feature-based representation also needs to store the point coordinates, but additionally also the features. We can now control the memory footprint by either changing the number or the dimensionality of our features. As long as our representation needs less elements to store than the raw point cloud, we achieve compression. For restoring the point cloud at a high quality, we use the chamfer distance as our loss function. The chamfer distance is the average squared distance between each point and its closest point in the other cloud. Computing this distance symmetrically for both point clouds punishes the network for either filling the whole space or leaving away certain areas. We do not only compute the chamfer distance between the input and the output, but also between input and each intermediate cloud of the deconvolution. This increases the quality of the final map and makes also the intermediate point clouds to lower resolution versions of the input. Our objective to restore the point cloud as accurate as possible does not require any supervision, and we can learn the parameters in an end-to-end fashion. We tested our approach on semantic kitty and new scenes. Therefore, we generated our dense input point clouds in 3 steps. First, we divide the whole map into multiple submaps. Second, we aggregate all points yielding the pose information. At last, we filter out redundant points using a voxel grid, and in the case of semantic kitty, we also filter out the dynamics to create a static map. This can be seen here. Now, let's look at the results. For all our experiments, we used a feature size of 3 and varied the number of feature descriptors to adjust the bitrate. On the top row, we can see the input point cloud on the left and Draco, the 3D compression technique from Google, on the right. On the bottom row, we see the Octave implementation used by the MPEG group and our approach for storing the coordinates and features with 16-bit floating point precision. We can see that our approach is, in contrast to the baselines, able to recover much denser point clouds. Our approach has no discretization artifacts but gets more noisy the lower bitrates are. For the quantitative results, we first look at the symmetric Euclidean point cloud distance, which measures the average distance between each point to its corresponding point. If we compare the red and purple lines, we can see that halving the memory footprint by using 16 instead of 32-bit precision is worth the small error increase. When comparing to the other baselines, we see that our approach is especially well suited when targeting very low bit rates. The next metric we will look at is the symmetrical orthogonal point cloud distance, which does not measure if each point is accurately reconstructed, but rather the distance to its nearest surface. Therefore, we compute the normals of the input map using the local scatter matrices of the points. This metric is less sensitive to the density, even though we can still see that our approach is able to outperform the baselines, which indicates that the noise level of our approach is of average lower than the discretization errors of the baselines. Many robotic applications, like path planning, use volumetric map representations to distinguish between free and occupied space. Therefore, the third metric we will look at is the volumetric intersection over union. The low density of the baselines, especially for low bit rates, leads to very few occupied regions, which reflects in having a low intersection over union. Our approach does not have such density problems, but the noise floods into neighboring voxels, which leads to occupying too much space. The noise of our approach decreases the higher the bitrate is. Let's recap what we have heard. We proposed a deep learning-based point cloud compression method. We use a fully convolutional autoencoder architecture, which can be trained in an end-to-end fashion. Our approach extracts a small number of feature descriptors, which can be used by the decoder to reconstruct the input. A novel continuous 3D deconvolution allows us to upsample the compact representation based on its geometric features. We are able to recover dense point clouds even when targeting very low bit rates. Thank you very much for your attention.